Okay. Can you hear me okay?
Yep.
Excellent. It's okay. Merci Andrew, merci Gianni pour l'invitation. My French is limited, so I will go back into English for now, I'm afraid. Sorry. So I'm here to talk about a similar subject to that which Andrew's just presented, which is coupling sort of machine learning models, in our case, namely PyTorch, though I will mention TensorFlow as well, to sort of Fortran models with a focus on, our focus is on the climate. And I should emphasize this is not just me, but sort of there's a large group at ICCS who've done a lot of really good work on this. So I should say there's the slides I've got online, and I think Gianni has a copy, so you can grab these and follow through any links at your leisure after the talk. So I'm from the ICCS, which is the Institute of Computing for Climate Science, and this is kind of a climate-specific group, particularly computational, at the University of Cambridge. And I think the idea is, as exactly as Andrew said, climate science now is not just kind of fluid mechanics or not just atmospheric dynamics, but actually it's bringing together high performance computing, data science, potentially machine learning, particularly where we're looking at. And really you need to bring together sort of people from all of these backgrounds and sort of bring them to work together to actually make proper or real advances. So this is the background to what we're doing. And the work I'm going to talk about today sort of grew out of this where we were looking at machine learning applications to be used within climate models or atmospheric models, and how we might sort of make this more reproducible and applicable to sort of more than one case, rather than being tailored, lots of people developing tailored solutions. And so similarly to Andrew, my background in this is I've sort of come from domain science. So I've worked in geoscience and doing simulations and numerical work. And I've been now working with sort of people who have specialisms in high performance computing, some in machine learning, etc. So climate modeling, I think, I don't know exactly the audience here, but hopefully everyone's reasonably familiar with the idea that sort of climate models are very large, very complex, sort of multi-part systems. So you'll have some kind of dynamic core driving your simulations, but then several parameters around the edge controlling things like microphysics or biosphere, sort of a biosphere model, possibly some kind of convection model, etc. And this is slightly different to how we might sort of think about traditional machine learning. So particularly deep learning is often, particularly in popular science, approached as this sort of black box model, where you feed it some kind of input, so in this case an image, and you get some kind of output that gives you kind of an interpretable answer that you are then left to do something with. And so what we're trying to do, or a lot of the projects we work with are trying to do, rather than having this kind of single black box sort of input to output, is actually looking at replacing part of a much larger physical model. So whilst the rest of the model, the core, say the microphysics, goes unchanged, we want to look at replacing one small part of this with some kind of neural net. And this might be for a number of different reasons. One example is these processes, particularly if we think about microphysics or radiation, are often incredibly computationally intense. So if we can sort of learn a neural net emulator that runs much faster, then we have the option to speed these models up, thereby sort of delivering your forecasts quicker or allowing us to run more ensemble models. The other possibility is using data-driven parameterizations. So at the moment, we build on physical models that contain some degree of approximation. One thing that people are looking at now is perhaps using observational data to build models that capture sort of additional levels of physics beyond those which are incorporated into the physical models. And one way to do that is to train a net on some physical data. And doing this brings a lot of challenges. So there's sort of physical compatibility. Often these these physics-based parameterizations or physics-based schemes will have a lot of physical constraints in to enforce reality. Neural nets, it's much harder to do this. So things like conservation laws. So that's one important thing. Another aspect is stability. So I think, as Andrew mentioned, even if you have a very well-trained net trained offline, when you put it back into your model, ensuring that it will remain stable long-term is not a given. And then finally, there's this sort of concept of language interoperation, which is what we're looking at today. So this is the idea that many of your machine learning frameworks or machine learning models are trained in Python, whilst a lot of these big computational models are written in some more sort of developed language, say Fortran, C or C++, and indeed often a lot of the climate and weather models are Fortran. So the issue becomes, how do we sort of bridge between these two languages? It's something that does require care and isn't necessarily straightforward, but it's also something that for those wanting to sort of leverage machine learning and deploy it within their models, we want to make it as simple and as straightforward as we can without having to worry about sort of deep aspects of computer science. So I'll take a look at a few solutions and then talk about what we've got. But before I do so, I think there's two types of efficiency I want to talk about here. The obvious one is the computational efficiency. So we want to develop a solution that is computationally efficient, runs quickly, sort of transfers data speedily. And part of this is due to the fact that we've seen in a few of the early attempts to do work and replace aspects of scientific models, whilst the neural net might be much, much faster, sometimes the data transfer associated with this, the overheads associated with that actually slow it down to a point where there may not be a gain. And this is indeed with sort of the ECMWF groups. This is a challenge they've had to try and get some of their machine learning aspects into the operational models. The other type of efficiency I want to talk about is the developer efficiency. So particularly with those working in research, we want to make it as easy as possible for people to be bringing machine learning into their work. We don't want to have people having to learn entirely new fields, delve deep into delve deep into computer science and sort of different frameworks, when really what they're interested in is using some kind of net within a model to learn some scientific results. So I would say really sort of the solutions we're looking for shouldn't generate any excess work for scientists and be sort of relatively straightforward to learn. We also, sort of from the HPC perspective, don't want to add lots and lots of dependencies. We want something that's going to be sort of easy to maintain and also something that's going to be relatively computationally efficient as well. So there's a few solutions. Perhaps sort of the most naive one would be to implement your neural net in Fortran. So we have seen some researchers who do this. They will train it in PyTorch, then save those weights, read those weights into Fortran, and then code up sort of matrix multiplications. And whilst this is nice because it does remove the two language problem, there's a lot of problems here on ensuring that you've ported your model correctly and sort of whether people are doing all the testing needed to check that, I'm not so sure. And then secondly, machine learning libraries such as PyTorch and TensorFlow are highly optimized, and probably more so than you will write. And whilst a lot of people are using quite simple ANNs at the moment, as sort of as this field develops, more and more complex features are likely to be incorporated, which are going to be harder to code up into Fortran. Another approach that we've seen is 4Py, or the C foreign function interface. So these are quite elegant, and they bring sort of Python types into Fortran. They're nice because there's just one pure Fortran module file that you have to add to your code, and then you need to link out to some Python runtime and Python environment. The downside of using these is that they're quite verbose, and there's again a learning curve associated with them. And as I'll come back to in a moment, you need to link against Python libraries and Python environments, which is not necessarily ideal in HPC situations. As Andrew's just spoken to us, we've got SmartSim, which is passing the data sort of between these workers through a network. And I think he did a nice way of summarizing that for certain architectures, especially if you've got you want to use GPU acceleration and GPUs are located sort of on different nodes, there's a lot of bookkeeping involved with sort of managing this data transfer, and you're going to have to do the data transfer anyway. So it's probably an ideal way for managing that. And the other advantage here is that it's incredibly versatile. So as he said, it deals with the data. You can sort of deploy whatever machine learning framework you wish, sort of at the other end. The downside from our perspective here was the sort of the learning curve associated with this, and then also the sort of data copying if you're doing CPU simulations. And then finally, I should mention the sort of Fortran Keras bridge, which is again, it's a pure Fortran implementation to access or to run TensorFlow models, but there's a problem that it's been inactive for quite a while and is somewhat incomplete with the more recent features. And then there's a couple of other suggestions there. So as I say, sort of the 4Py approach that we were looking at originally is this idea of taking your Fortran data, passing it out to Python runtime, which will then be passed to some Python work to run the inference, and then after running inference, the data will be passed back up to the Fortran. And as I said, managing Python on a HPC environment is not ideal. I think there's an XKCD comment that sums this up quite nicely, which is that it can be very difficult to get the environments right, to link things correctly, and so it's advantageous, we feel, if you can bypass the PyTorch and go directly to the underlying frameworks. And so that's where the work we've been doing on FTorch comes in. Both PyTorch and TensorFlow have C++ backends with APIs to access sort of the underlying codes, and binding to Fortran binding to C from Fortran and through C to C++ is at least well supported, if not completely straightforward in Fortran now. So the approach we're going to take is we save our PyTorch models as torch script. So this is a utility from within PyTorch itself, and this is kind of a static type subset of Python, and it's essentially saving things as this intermediate representation or a graph representation of our neural networks. And these can then be run by anything that's got some kind of API into the underlying Torch code. So what we've done is we've sort of produced this Fortran API, or this Fortran library, that will take these Torch script models and pass them through to Torch, running inference through the C++ code. So from a computational perspective, one nice thing about this approach is that we can do this with no copy access in memory. So we know that within HPC or within computing, one of the most expensive operations you can do is data transfer or data copying. So here, hidden away under the hood with some sort of clever use of pointers, we can take Fortran data that is stored in memory, and we can then pass that as a pointer to PyTorch. and PyTorch will then use this to access sort of the data that's the Fortran data stored in memory, run the inference, and then sort of return it to Fortran, all without needing to do any copying, which is quite a nice aspect. And we can also address the sort of row major, column major question that often comes up. Sort of again, I'll speak in a second about some of the work we've done to help users with this, but you can also sort of get around this with Torch accessors. So there is some control that we provide to the users to manipulate row major, column major, if they have something particularly exotic. So in terms of using the installation, we've done via CMake. So the process for this is to install PyTorch or libtorch, which is available as a download from the PyTorch website. We then clone our library, build it using CMake, install it using sort of the CMake install scripts, and then it's a case of linking to whatever application you want to bind it to. So this is particularly nice for the work we've done on sort of HPC systems, is it can be cloned and built sort of alongside the code. And then we provide some guidance on linking in the same way you would do to any other kind of Fortran library like NetCDF or MPI, etc. And we've been using this predominantly on Linux, but we have done some work with macOS and Windows users as well to try and get this working. So provided in the Git repo, which I think is linked at the end, as well as the source code for all of this, we've also got some examples which guide through the sort of users through the entire process of how to save a Python model into TorchScript and then how to link it and run it in Fortran. And at the moment, these are kind of a very, very simple example with a net that multiplies a vector by 2. We also have an example with using ResNet 18. And finally, a sort of more scientific-based gravity wave drag example. And then alongside the code, we provide some tools. So particularly this PyTorch to TorchScript script or file, which is sort of outfitted for helping users save their models to TorchScript ready for deployment in Fortran to sort of ease this transition. So in terms of other things, the library, I say it's open source and freely available. It's on GitHub. And one of the nice things about sort of working with the API is that we should be able to support future development of PyTorch, assuming that libtorch continues to support those features. So I'll quickly look at some code. So in terms of saving models to TorchScript, this is all done within PyTorch, and it's done using this, we sort of call this traced model. So there's this torchjit trace method for those familiar with PyTorch, and you can then just call this save method, which will save it to sort of a binary file as TorchScript. Then if we wish to load that, so that saved model we've got, if we wish to load that into Fortran, we use the ftorch library. We define a type which we've created. There's this torch module type, and then loading from TorchScript, it's as straightforward as just calling the torch module load with the path to that saved TorchScript file. If we want to create some tensors, again, so here's the script, or here's the code that would be needed to do that. Again, we're using this ftorch library as sort of a linked library. To create the torch tensors, again, we've got a bit like the module, we've got two types, we've got a type called a torch tensor, and we define them for the sort of the inputs to the model and the data that will come out of the model. And then to cast these Fortran arrays, real Fortran arrays, to cast them to these format, we've got this method, the torch tensor from array, where we pass it our data, a layout, and then the device that we want this to be running on. the CPU. And this will deal with all the conversion to pointer and casting ready to be passed into the call to the PyTorch API. Running the model is just as straightforward as calling this torch module forward function with the name of our model, the tensors we're passing in, and the data we're going to get out. And then to clean up afterwards, because we need to do memory management properly in within Fortran, there are these delete methods which will clear away anything we've had in the memory. And then the out data is immediately available to be used from the Fortran without having to do any sort of recasting or data transfer. It's immediately ready for us. So the whole code, this is sort of adapted from the ResNet example, but the entire code for running ResNet within Fortran looks something like this. And then for GPU acceleration, the only changes we need to make here are to save the model for GPU, which can be done by selecting the CUDA device and then casting the model and the data we use to trace to CUDA before we save it. And by doing that, it will then save it from the model. And similarly in the Fortran, all we have to change is the device that we wish to cast our input tensor to when we set it up like this. So the whole idea of this is that we want to develop a library that is sort of familiar to both PyTorch and Fortran users, and sort of abstracts away a lot of the complicated computer science, the pointers, the transpositions, etc., to make it sort of easy and familiar for people to deploy in their particular applications. So one place we've used this was as part of a atmospheric model. So this is the MEMA atmospheric model, the moist atmosphere. And there was some work that was done by Zach Espinoza et al. And they had been using an emulation of an existing gravity wave scheme, so for calculating drag within the atmospheric flows. And this was a multi-layer neural net that had been trained offline, and they then wanted to put it back into the model to sort of demonstrate that emulation was possible. And one of the issues they had was it was running extremely slowly. So they were using this 4Py library to connect, and they were also initially running this in TensorFlow, and I'll maybe touch on some of the differences at the end of the talk. And they approached us to sort of ask about how they might go about speeding this up, making it more efficient. And that's sort of initially where this work that we've been doing since has grown from. So the results were that it was indeed possible to emulate, and it was possible for a model to run sort of for multiple years in a stable sense. So here is the sort of zonally averaged winds around the equator, showing the quasi-biennial oscillation. So this is a sort of change in winds or a reversal in winds, which is this sort of transition between the red and the blue that occurs within the stratosphere. So sort of around this level in the atmosphere. And it happens on sort of a semi-regular sort of 28-month roughly cycle, that the winds reverse from blowing eastwards to westwards. And so this is the results with the sort of original gravity wave parameterization. And then these are the results with the neural net emulation. So you can see there are some slight differences, but the net does remain stable, and it reproduces the quasi-biennial oscillation, or the QBO, which is traditionally something that is quite difficult for a lot of models to capture. And so I would say if we look at the differences between the plots, you find that we do tend to kind of over and under predict. But this is something that's discussed a lot more in Zach's paper and is here for sort of scientific context. Our focus was sort of more on the coding side of this. So in terms of making it easier for for the users. We sort of redesigned the coupling that they had using 4Pi using FTorch library instead, and found that we could reduce their sort of boilerplate code from 45 lines down to 27. But also within this, it was sort of a much more intuitive, much more, should I say, PyTorch Thonic implementation of the code. And there is a fork of the Mima model with these deployments in available on GitHub. Again, looking at sort of some of the computational side of things, we did some checks for strong scaling. So this was on Wilkes 3, which is the computer we've got here in Cambridge, and is a tier 2 system. And this was using AMD CPUs alongside an NVIDIA A100s. So what we've got are results for coupling varying numbers of cores alongside one GPU. And we then ran the model using both sort of the CPU inference and then GPU accelerated inference. And the results we get are that sort of as we increase the number of cores, the time spent in the CPU simulation, the CPU neural net drops, which makes sense because we're operating on smaller quantities of data. But interestingly, sort of the time spent within the GPU neural net increases. And this is likely because for low numbers of cores, you're doing data transfer sort of only 4 times for 4 cores. But if you've got 32 cores, you're transferring sort of 32 segments of data. And as we said earlier, data transfer is particularly expensive in these simulations. If we look at sort of the total simulation time, we can see that sort of as we increase the cores, the solid lines here come down and sort of reach some level of plateau. And interestingly, when you sort of account for the GPU acceleration versus the overheads of data transfer, the two are actually quite similar. Again, if we look at the percentage of time that's spent within the neural net emulation, the CPU, since it scales well with being on the same architecture, is relatively stable at about 6% of the simulation time, whereas the GPU, as you sort of add more and more cores, you add more and more sort of data transfer overheads. So this would suggest that probably when you're looking at doing HPC simulations and accelerating with a GPU, it's a good idea to implement some kind of MPI gather calls to sort of gather your data before you pass it off to a GPU. And this is something we should probably perhaps look at doing in future with our work. Sort of off the back of this, we had some more detailed benchmarking. So we took both the drag routine and the ResNet routines that we've been looking at and passed them, did some detailed timing. We found that sort of using OpenMP helped speed up CPU calculations. And this is likely because of the optimizations that are sort of written into PyTorch. And again, emphasizing the fact that using the sort of the API straight into PyTorch, there's a lot of stuff under the hood in there that's going to speed up your simulations that you're not necessarily going to get if you try and write it out just in Fortran, say. We see that there's a limited effect on GPU when using OpenMP. And there's about sort of a 30 times speed up for one thread when we go to GPU. But if we look at using sort of the CPU with 8 threads, when we apply 8 threads to GPU, it's closer to maybe a 10 times speed up. So again, that's also worth bearing in mind. And there's no simple silver bullet of saying, let's just shove it on GPUs. There's a lot of sort of testing you need to go through and sort of working with HPC specialists to kind of work out these optimal aspects. So I think in conclusion, there's a few takeaway messages, largely very similar to those that Andrew presented. This is a very sort of fertile land at the moment for using machine learning to sort of accelerate or improve scientific computing. and it needs this interplay between a lot of these specialisms within computer science, domain science, etc. Our library we're targeted at making it easy and efficient for researchers to be able to deploy PyTorch models within Fortran with sort of relatively small changes to their existing codes and trying to keep things familiar. And for I've hinted a couple of times, we also did some work looking at TensorFlow, and we do have a library similar, but we find that PyTorch just couples much better and is much faster and is much easier to develop in. So in general, if scientists are looking at developing new projects, we suggest PyTorch. So finally, some future work, we're continuously working to improve things, and Elliot, who I think is on this call, has done some fantastic work with us recently on a placement. We're potentially considering looking at bringing inference into the model or into the library, because online training is likely to become important particularly within climate modeling for building stable models. And finally, we've got some ongoing work looking at using this library to couple to the CESM model. And we're always open for collaboration, much like SmartSim. And for those who are on the Calypso project, please do consider booking a ICCS Code Clinic if you want to discuss some of these things further. So finally, I will be convening, along with a couple of other Vesri people and Alessandro, who's from HP SmartSim. We'll be convening a session at the European Geosciences Union in April. The abstract deadline for this is 10th of January, but it would be good to hear from people there. And again, at the Scientific Computing Platform in Switzerland in June, we're hoping to have a mini symposium on this topic there as well. So I'll finish with that. There's some links here, and like I say, all the links can be found in the slides on the website. So yeah, thank you very much.
Thank you very much, Jack, for this very clear presentation about different tools, and also the PyTorch with the examples, with benchmarking, which is very nice. So do we have anyone having any question, please? Okay. Maybe I have a few questions. So I was, I mean, because I never used the PyTorch. I suppose that this tool works also very well on to be for the coupling with the climate model on HPC. I mean, multiple nodes, multiple processes. Maybe.
Yeah, so we've used it. Initially, we were using it just as a CPU model, and we found that worked very well, because you can run the net on exactly the same thread or exactly the same process, and the data transfer is, well, nominally there isn't data transfer, you're just operating on the same data within memory. Running on GPU, again, this is largely work that Elliot, I mentioned, has done a lot of efforts on recently. So we found that